Hey guys, welcome back to my YouTube channel. So we are still on gamma functions. So I said on our next video we're going to be treating how to calculate gamma functions of some fractions or negative functions, right? So the formula is just entirely different, but it's actually the same formula we have been using. So before we go to gamma functions of functions and negative values, let us evaluate a constant. Now, what is that constant we are going to be evaluating today? We are going to be evaluating the proof of gamma 1 over 2 is equal to square root of pi. So this is the basis of our concern before we enter the gamma functions of fractions and negative functions. So now we're going to be saying they said the gamma functions, let me put it that way, they said the gamma function of half is the square root of pi, which let's assume we don't agree with that unless we prove it. So now let's prove it. So in order to prove it, we know that the general expression for the gamma function of n is what? General expression for gamma n, let's call this step 1. General expression for gamma of n is equal to the square root integral coming from 0 to infinity x raised to power n minus 1, right? Then exponential minus x dx, right? So now we're going to be saying, okay, now since they ask us to prove for gamma of half, let's substitute n for half. This is 1 over 2 equals integral coming from 0 to infinity x raised to power 1 over 2 minus 1 exponential minus x dx, right? So now let's proceed. So half minus 1, that is integral coming from 0 to infinity exponential minus half, right? Then exponential minus x dx. So now I move to what I call my step 2. So let's call this step 2. Step 2 goes like this. Let x be equal to y squared. Now there's something I'm trying to work on here. I'll really fill you up and you really understand why I'm saying let x should be equal to y squared, because I'm trying to get an exponential of a powered function, because I know that an exponential of a powered function I can easily express it in I can easily express it as a rectangular and a polar as I can easily express it in rectangular and polar coordinates. You really understand what I'm trying to say. So now let's proceed. So I say my step 2 goes like this. Let x be equal to y squared, right? So if x is equal to y squared, the x is equal to 2y dy, right? So now let's substitute it. So we have gamma function of half is equal to integral coming from 0 to infinity x raised to power minus 1 over 2 exponential minus y squared, right? Then this is 2y dy. So this gives me 2 integral 0 to infinity y times y raised to power minus 1 gives me y plus 1, right? Exponential minus y squared dy. So now y plus 1 is 0, right? So this is 2 integral coming from 0 to infinity, right? Y raised to power 0 exponential minus y squared dy. So y raised to power 0 is 1, right? So this is 2 integral coming from 0 to infinity exponential minus y squared dy. So I move on to my step 3. Now step 3 goes like this. Let I be equal to the integral coming from 0 to infinity of exponential minus y squared dy, right? So now I'm going to be imputing another variable. Now I'm going to be assuming another variable, right? And that variable I'm going to assume is the horizontal component of a Cartesian coordinate. Remember, I've used x to be equal to y squared. So if I use x again, it might confuse you guys. So naturally, I'm supposed to use x. I'm supposed to use another variable with y, and that should be x. But since I've already started using x here, then let me just impute another variable. So now let's say let's use another variable for this. So this is y integral comes from 0 to infinity exponential minus u square du. That is my variable 1. Let's call this I1. Then let's say I2. Let me use another variable, is integral coming from 0 to infinity exponential minus v square dv. Right. So now let me assume this is my vertical component variable, and this is my horizontal component variable. Let's call this v vertical component, and let's call this horizontal component. Right. So now let's continue. So now I'm going to be multiplying these two integrals together. So if I multiply these two integrals together, this gives me I square, right? Now they are the same thing, but okay, instead of me saying let this be I1, I2, let's just call it I, because it's just basically the same equation but just different variables. So let's call this I and I. So I can be expressed as this, I can also be expressed as this. So when I multiply it together, multiply I times I gives me I square, right? So multiplying these two also, this gives me integral coming from 0 to infinity, integral coming from 0 to infinity, exponential minus u square dot exponential minus v square du dv, right? So I square is equal to integral coming from 0 to infinity, coming from 0 to infinity, right? This is exponential. Now when I simplify that's taking minus at the back, we're having u square plus v square du dv. Is that understood? So this is what I have. Now, like I said, we can easily express this function as a rectangular coordinate and a polar coordinate. Then change the because now this is just expressed in rectangular coordinates. Now let's express it as a polar coordinate. Now what I mean by is expressed as a rectangular coordinate, now this is what I mean. Now we said this is our x and y axis. Now in this case, now we used v and u, right? So this is my v and u axis, right? So now let's assume there's a small strip. The distance from here to that strip is u, while the width of the strip is du, right? So for the vertical side, the upward distance from here to the strip here is v, and while the height of the strip is dv, right? So you have du and you have dv here. So the area of this strip now gives me, let's call it the A, is du dv, right? Now this is straight line, right? This is let's draw this straight line here to form a rectangle, and let's draw this and let's call this r. So this is a rectangle, right? This r, and this is u and this is v. So we know that r square is equal to u square plus v square. The normal Pythagoras theorem. Right? So this is r square is equal. So now this is what I mean by a rectangular coordinate, because you can see this here and you can see this here. So now let's express this as a polar coordinate. Now when it's a polar coordinate, you'll be having something like this, right? And this is, let's call this r. So now I decide to rotate this at a very small angle. Let's call this from here to here. I rotate this from here to here. Let's call this d theta, right? Now for example, there's a small tiny strip that has no there's a small tiny strip that is not actually thick. So when I rotate it, it forms something like a mesh. So I rotate it like this, it forms something like this as the distance covered, right? So this from here, so this is r and the distance, right? So I can call this place r times d theta, right? This is like this is the length, and when I rotate it, the distance covered, right? So this is r d theta. So then let me draw a vertical line here. So remember, is the axis we are using is u and v, right? So this is u, right? From here to here is u. So now let's from here to here, since from here to here is r, the remaining, the smaller thickness, let's call it the r, right? So now this is, let me assume this is a rectangle, right? Which is not actually a rectangle, but let's assume it's a rectangle. So this is my height and this is my width. So the area becomes r d theta dr, right? So now let's call this is my vertical component, right? This is v and this is r. So using our same Pythagoras theorem, r square is equals to u square plus v square. But you see, the only difference in this is that their areas are different. So now we are going to be, instead of me using this area here, I use this area here, right? So I'm going to be exchanging. So since the a is equal to du dv, and the a also is equal to r dr d theta, right? Then let me use this. That's what my mean, changing from rectangular to polar coordinate. So remember, my I square, this is my step 4 right now. My I square equals integral come from 0 to infinity exponential minus u square plus v square du dv, right? So since u square plus v square is equal to r square, right? Let's substitute here. Now before I go there, okay, let's substitute here. We'll be having integral come from 0 to infinity exponential minus r square du dv. So now before I substitute this area for this area, now let's check, because we are involving two variables, right? And we know that the two variables we are using before, at u 0 to infinity works, at v 0 to infinity works. Now let's check if, so what we actually work now at r and at theta. Now what I'm trying to say is that given, so what will actually work for r and theta, so it is said that, because since this is a rectangular coordinate, the limit of r will be only from 0 to infinity, right? But since theta is a polar coordinate, remember we are involving two variables, which is r and theta. But since theta is a polar coordinate, theta will be limited from 0 to pi over 2. So when we substitute this, instead of us using 0 to infinity 2 times, we'll be using 0 to infinity for the r variable and 0 to pi over 2 for the theta variable. So now let's substitute this area we have here with this. So we'll be having integral. Now since theta is going to be my last variable, let's call it from 0 to pi over 2. Then this is theta coming from 0 to infinity exponential minus r square, right? So this is, between this for this is r d theta, right? So now if you look at the previous problem we solved on gamma function, I said when you have a powered function in gamma function, express it as u, and this is like what I call a powered function. So now let's say u is equal to r square, right? So du dr, so I call this my step 5. So du dr right now is equals to 2r. Now if you are following me step by step, I'm sure you are really understanding what I'm doing. So this is du dr is equals to 2r, right? So now let's put it here. We have integral coming from 0 to pi over 2 integral 0 to pi to infinity exponential minus u r d theta, right? So what am I trying to do here? So since we've expressed this to be this, so my dr here, let's make the r subject of formula. So the r is equal to du over 2r. So let's substitute it. So remember we are working with just the r variable, right? So we can just easily, since we are working with the r variable, we are taking this one. I've solved the question like this on my channel. You can look up the link is I solved the question on complex integrals, and I really explained how to go about it. So first, naturally, before we started, we would have just take this one, and that's exactly what we are doing. So we say let u equals to r because we are working with the r variable. So we are not actually working with the theta variable right now. So it's just the r variable we are working with. So, and since we said the r is equal to u over 2r, right? Then we substitute it here. We have integral coming from 0 to theta over pi over 2, integral 0 to infinity, right? Exponential minus u r du over 2r, right? Then this is the theta. So now let's just bring this one now since we are working with it. So this is theta. It's an integral comes from 0 to infinity exponential minus u r dot du 2r. So r cancel r, right? So we're left with integral comes from 0 to infinity, right? Exponential minus u du. So you see we can easily integrate it. We can easily integrate this, right? So remember now since this is 2r, so 2 is going to the back of this, we're having half. So since we can easily integrate this, right? So integrating exponential of minus u2 before we input our limit. So integrating exponential of minus u2, that's the same thing as minus exponential minus u, right? Just like taking this here, dividing. Remember, to integrate an exponential of mx, we just exponential of mx over m. So taking the value that is before the x and dividing it. So the value that is before you here is minus 1. So divided by minus, so dividing exponential minus 2 by minus 1 is the same thing as this, right? So applying our limit. Okay, half times this, right? So this is minus over 2, right? So applying our limit from 0 to infinity. So applying our limit from 0 to infinity, right? So if exponential of infinity, so it's just like this is what I'm saying, minus exponential minus u over 2. So apply, you use the infinity first, then you minus it, minus exponential minus u over 2, then you use the 0. Right. So exponential of infinity is what? 0. Exponential of infinity is only 0. So we have 0 here. Then minus exponential of 0 here. Now since this is minus, right? So exponential of 0 here is 1. So you're having minus 0, or which is also 0, divided by 2, right? So exponential of 0 is 1. So we'll be having 0 minus 1 over 2. So which gives me 1 over 2, right? So this is what I'm having. So this is what I have for when I solve the r variable, right? So now let's remember this is what I solved when this is what I got. The value I got, that's 1 over 2 when I solve what is in this bracket. So now let's replace it with what is in this bracket. So our answer was 1 over 2, right? So this is my step 6, right? Yeah, my step 6. So this is integral comes from 0 to infinity, 0 to pi over 2, right? Half the theta, right? So integrating half right now. So integrating half, which is actually a very, very simple first. So before we integrate, we have to before we input our values, we have to differentiate. Sorry, before we input our values, we have to integrate 1 over 2 d theta. So integrating 1 over 2 d theta, that is integrating half the theta gives me theta over 2, right? Integrating the theta, that theta half is a constant, so this is theta over 2, right? So imputing our limit theta over 2 from 0 to pi over 2, right? Theta over 2 from 0 to pi over 2. So what will I be? So imputing our limit, that's between 90 degree. Remember, pi over 2 is 90 degree. So you put in 90 degree for this. So let me just split it up so you can easily understand. So this is theta over 2, pi over 2. You put pi over 2 first, then you minus it, theta over 2, and put 0 in. So putting 90 degree here. So this is or you can put in theta over 2 here. Remember, 90 degrees only when you're using it with a trigonometric trigonometric function, which is like sine, cosine. Then you use 90 degree here. So but this right now is in radians. So you can't use 90 degree. So you can only use 90. For example, if this is cos theta, or minus sine theta, then you say okay, theta is 90 degrees. But since this is in radians, this theta here is in radians, so you just use pi over 2. So this is pi over 2 over 2, right? Minus when theta is 0, so this is 0. So our answer is pi over 4, right? So remember what we assumed. We said, remember that when we multiplied the two integrals, we had I square, right? So all what we have been solving is equal to I square, right? So then our answer is I square equals pi over 4, right? So square root in both sides, so my I is equal to root pi over 2. Now also do not forget that before we started splitting up our variable, so if you remember, before we started splitting up our variable, we had this is the answer we got before we started saying let I be equal to this, right? So we had 2 in the back of this answer, so our final answer was going to be affected by these 2 right here. So now let's put it back. So we having, so I right now is equal to 2 integral 0 to infinity exponential minus y square dy, right? Sorry, what we are integrating, which is, sorry, the gamma function of 1 over 2, not I. So gamma function of 1 over 2 is equal to this, right? Remember, I was this one. So, and we said integral comes from 0 to infinity exponential minus y over 2. We got it as this, right? So this is root pi over 2. So we just input it back. So gamma function of 1 over 2 is equal to 2 times root pi over 2. So this gives me root pi. So we can now say, okay, yeah, that assumption is correct, because we have been able to establish the fact that gamma function of 1 over 2 is equal to root pi. So now let's go to gamma function of fractions and negative functions. So thank you guys, which will be on our next video actually. So thank you guys for watching, and please subscribe. Peace.